Yeah, I'm all set.
All right, oh, Jesus. All right, everyone, thanks for coming back. This is track 2, even though it's not marked, and it will remain to be track 2, and it will be marked at some point. And so I just wanted to thank everybody again for coming to DerbyCon. Thank everyone for coming back after dinner and not going to the bar. The bars are open until 4 a.m. There'll be plenty of time for that later. And anyway, here we go. What's this talk called? Sploit me if you can.
Those of you who thought that this was Chris's track, we have you now. Actually, Chris and I have this thing going on. I think that my crew is going to be louder than his crew, so let's all let him know that. On the count of 3, everybody yell, exploit. 1, 2, 3. Exploit! I think we owned him. This talk is called Exploit Me If You Can, or Exploit Me If You Can. It is about a capture the flag qualification round challenge. If you do not know what hexadecimal looks like, you're in for a treat. I personally think that it's one of the most beautiful things, green on black hexadecimal. Let me hear it. Who's with me? Oh yeah. That can only be topped by hardware porn, which I do produce quite a decent amount of quantity of.
Illegal, I mean,
No. The NDA stuff stays in my own personal repository. The stuff that I share, I can share publicly. For those of you who think that I'm some sort of kiddie pornographer, no. Hardware porn being... All right, on 3, lame. 1, 2, 3. Lame! Chris and I actually decided that we should drop the wall and just turn this into one big talk where we compete. The staff didn't go for it, sadly. Who am I? I'm a curious technoid. Defender, offender, some people call me offensive. I'm a daddy, husband, and a hobby farmer. I just picked up a goat, and my wife right now is like getting seriously buff, going, It's tough work. I'm a singer, I'm a biker. I don't pedal a whole lot, but I do lots of vroom vroom and horseback. Who cares? Right. Okay, the ones that you probably care about is VMware fears me, Smart Grid fears me, hardware fears me, Capture the Flag fears me, and I produce hardware porn. But I'm really a nice guy. This year's Capture the Flag exploit is going to lead us into some of the more interesting technological advances in anti-exploit technology. A little less than I originally thought, but we'll get into that. Used to be. Who remembers the golden days? Back, didn't even get there. Let me describe the golden days. Then you can say, oh yeah, that was me. Probably around like WinNuke era was the start of this good stuff. But basically, you have buffer overflow. You overflow the return pointer. You stick shellcode somewhere. And then, well, since you didn't really want to spend all the time getting it in the right place, you'd stick an ops let in, hit shellcode, you'd have shell, right? Right. That was about the time Metasploit started coming on the scenes and tying all this band of rabble together and saying, hey, let's provide something that was reusable. Excellent. So we got smart. We said, that shellcode's ending up in data. Heck, we have whole hardware platforms that separate code and data. We can turn this Intel platform into that. So we created the NX bit. Don't execute this crap. You can create pages of memory that simply the processor will not execute code from that page of memory. But we soon proved to them that this was insufficient because we found that libc actually provided all the functionality that we really wanted in the first place. And so we returned into libc, or what's become known as return-oriented programming, which is like the next generation where we find all sorts of interesting widgets, not just in libc, but in everything. So they say, okay, well, if they can create a stack that then returns through and does their stuff anyway, let's make it so they can't find it. Let's randomize it in 12, 13 bits of entropy, that sounds great. Stick it in the high bit numbers so that, it's not even close. We're great. But what if we can find stuff? This is probably old hat for most of you, but it's a great setup. I don't have enough time. I could not cut this thing down any further, so I'm going to blow through the next couple slides. They will be there for you. Basically, if we're looking for whether a library or binary is set up to do ASLR on Windows, turns out there's some Python stuff that can spit out, hey, this is ASLR enabled. On Linux, we got a couple more nasty ways to find out. But the meat of our talk, capture the flag, or every year DEF CON throws, arguably, okay, I'll take criticism, but arguably one of the best capture the flag games in the world. Capture the flag not being things that you run around with a paintball gun or with a little Velcro flag attached to your hip, but the idea of raw ponage for the purpose of gaining points and thwarting your enemies and friends. So the game is so popular that they've had to move to a qualifying round to weed out the hundreds of teams that sign up every year because they have to keep it doable. So they limited it to like 10 or 12 this year. Qualification round, however, has become an entity in and of itself. I remember the first year I played, there was just one box, and you had this web GUI that got you into directory traversal thing that gave you a password, which gave you a flag, which also gave you a crackable password, which got you almost out of the box, but it actually spit a binary out at you, and then you had to hack like 5 binaries to qualify. That was a lot of fun. It's become this Jeopardy-style board game with some craziness involved. It's huge. It's got categories from forensics to ponage to binleetness, binary leetness, and trivia and grab bag. And there's a lot of good stuff in here, and there's a lot of crap. But that's not to say that I criticize the guys. They do a great job, and it's not an easy thing. Typically, the creme de la creme of the whole thing is Ponage 500. Because if we're doing capture the flag at all, we want to own, right? That's a nod. There's a correct answer. This year was no different. Ponage 500 was indeed one of the most challenging and interesting things in the entire game. A few of the details about it. It's an interactive text application, so you can exercise netcat or a Python connection to it, and it just spits back text. You interpret the text, you interact with it, blah, blah, blah. It uses C++, so we're talking object orientation, with templates. We're talking insanity and stupidity. It's kind of like a database application where you can add or upload new records, you can edit the records, delete the records, download the records, view records, and view a summary of all the records that you've created. Pretty cool stuff. Because of the dynamic nature, it pushes a lot of the data is placed into the heap. If you guys are familiar with heap structures and the way that heaps move around and grow and do all sorts of dynamic memory management, awesome. You're going to enjoy this talk even more. The rest of you, this will be an interesting thing. Occasionally, when we upload a record and then we update a record, things go boom. The socket gets terminated, the program goes away, and, well, we have to try again. Kind of odd, because it only happens some of the time, regardless of what we did. I mean, you do the exact same thing over and over and over, and about 50% of the time it worked, and 50% of the time, everything went. Worse yet, we found that depending on what version of Linux you're running, Ubuntu, CentOS, because I started on CentOS, Fedora, things behaved a little differently. Kind of strange. We tested on CentOS and Ubuntu. We made really awesome stuff happen, but we overlooked one small but vital piece of information. We were so interested in getting the binary to work, we missed the fact that it has a dependency on libcrypto.so.10. A quick Google search turns up that the only distribution that had that particular file that I found was Fedora. And that's the one that we didn't focus on much at all. So we're going to focus on that one for the rest of the talk because the exploit was written for that in mind. A little bit of the application at a glance. On the right-hand side, you see a netcat session. Connection succeeded. Enter password. Oh, wow. It's password protected. Well, let's skip that part for a minute and just notice. We have the ability to upload, edit, delete, download, view record, view summary, and quit. The annoying part is that you'll notice that they're randomized in order. So you can't just say, oh, I want to upload in this thing, so that's number one. You have to parse everything and decide which one you want to use. So you'll notice in this first hit, upload was number 6, upload's number 1, upload's number 3, and number 3 again. And they just kind of jostle around. Whoops. You have to bear with me. I'm double fisting this presentation because my clicky thingy has a dongle thingy, and dongle thingy went bye-bye. I have no idea where it is. So I'm doing the mousy thingy in this hand and the pointer over here because I got to have my laser pointer. The people that I learned how to present from said, hands at your sides, nothing in your hands because they become a toy. I have 2 toys, baby, and you can suck it. So the challenges for Ponage 500, password protection, standard lib C++ templates, stack and heap randomization, a fork hack, which we'll talk about in a minute, so that each child gets new maps. We'll talk about that in a second. Random selection of a C++ class so that it kind of only works some of the time. Random menu, suck. Unknown Linux environment, and we call chroot. Yay! Well, after analyzing what caused the crashes, we found that there are 2 different classes that are selected at add record time, randomly selected, and one of them, these are C++ classes, so they have member functions. You guys are all familiar with C++? The member functions are a list of things that you can do that know how to do something with this class. Pretty cool? Well, one of them doesn't know what to do with this class, so it does an overwrite beyond the end of this class, this object. So the overwrite, or the update, writes hex F8 bytes regardless of what you send. If you send it 3 bytes, if you send it hex FO bytes, whatever. But the buffer starts only E8 bytes away from the end. So what's that give us? Buffer overflow, how big? 16 bytes, or 10 bytes. I like to just cut out the conversion, so I think in hex now. So our overwrite, this is a disassembly in the program. I call this dirty overwrite. Did I skip one? Because I thought I showed the, nope, that must be later in the course. So here is our write loop. We loop. So we come into the function, blah, blah, da, 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 we set up some stuff, blah, 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 blah. We set up a local, and then we jump down here, and it says, hey, have we written 62 times? No? Okay, let's jump back up and loop. We set up our local variable address pointer into EAX. We set up our source address into EDX. We deref EDX into itself. So it's like into EDX. And then we shove EDX into the deref memory address where EAX points. Awesome. We increment both. So we're doing D words, not byte for byte. We go bloom, bloom. We increment both. And we add to the counter. Then the counter again is checked. Hey, have we done this 62 times? No? Okay, loop back. So you can see how this creates what's called a write loop. And a little before and after action here. Again, I told you, if you don't like hexadecimal, don't leave now, but you can endure it. All right? Good. So this is how our object is laid out in memory. It terminates right here at the F9. The F9 is actually something that is part of the malloc heap metadata. So we start here, and the first D word is an address. What do you think that address is? Close. It is a virtual function table pointer. So remember those member functions that I was talking about before? They are in a function table. I'll talk about it in a minute. And this, right here, points to it. So here's before our overwrite. And here's another virtual function pointer table pointer. And after our overwrite, see all the 414141s? I skagged this image from something later in the talk, so it might not be readily apparent because I did not. I chose to actually overwrite with the same virtual table pointer, but I changed the next number from 0e to 0x200. Remember that. And we have our overwrite. So handling the challenges along the way. Password protection. Who here thinks it's a great idea to hard-code the password into your program? Lame. Yeah, I like that. That's very good. Turns out, during our, we read in bytes, and then, oh, wait, our disassembler actually goes and says, that's a string. I'm going to name it part of the string. Have fun, bitch. Oh, well, yeah, no, that's not my disassembler being sassy. That's actually the string in the binary, blah, blah, blah. Somebody running strings could find this. That actually brings up other attacks. Cutaway, you still here? Oh, dude, he ditched. Oh, well. C++ templates actually proved to be one of the more painful parts for me personally, because I've never reversed anything that uses C++ templates. So this was kind of like, how do I even Google for that? However, I will tell you, let me back up one. Notice, right here, blah, 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 ZNKSS7 compare. Yuck. Particularly when you consider that it actually translates, when decoded properly, into standard library, string, compare with an char constant pointer as an argument, and it returns a const. Okay, yeah, how'd you get that from? Oh, whatever. They're even worse. So here, who can tell me what that is? Not looking at this. Yuck. This actually ends up being a destructor for an object. So with object orientation, you have a constructor and a destructor. It's like basically what gets run to initialize this thing when we first create it, and what do we run before we throw it away, just in case we had maybe something tied to a file descriptor or anything else that needed to be cleaned up. Well, using C types and Python, and if you don't program in Python, start, we can pull in the libc std C++. You guys have seen that probably in your Linux directory listing, right? Lib std C++. No, it is not venereal disease. What it is all the stuff that makes C++ work really well. Baked into this thing is something called under cxa under demangle. Demangle? Interesting. We hand in this, and it just spits this out. Yay! This made things way easier. Sadly, I found this way too late to make my life easier, but I thought it'd make yours easier. The next challenge, fork hack. So you guys have probably written or read some code that did a forking server, right? So you have a socket that accepts a new connection by calling accept, and it just kind of sits there and waits until somebody connects. And as soon as somebody connects, it says fork. That creates a completely separate copy, nice shirt, of the same running parent process. and it's a child that then goes off and handles that connection. Okay? Well, when you're forking, it's an exact copy. So the same randomization that hit you in the parent gets handed off to the child. So if you hit 50 children, you get the same randomization. So what they did was they forked, and then they executed themselves again, the same process again, but this time handing in a parameter, a socket number. So the child gets created, execs itself again, hands in the socket number, and then it gets a whole new set of randomized maps, and it still has a copy of the socket so it can communicate and handle the services as necessary. It's pretty cool, actually. Could have been worse. So fixing this really didn't help our exploit because, well, the exploit has to be thrown against something we don't control, right? I mean, if we could fix all the stuff that makes it hard to exploit before exploiting it, that'd be really cool, but we can't. However, our randomness, we now need to take a peek into memory. We'll talk more about that in a minute. So here is the disassembly of our fork nonsense. Here's the except, if you can read the really light blue up here. And then our fork, and then all of this madness right here is basically setting up a new command line with a file descriptor at the end. It hands in that information into sprintf, and it then calls exec on that new string, and then we get into all the goodness. When main is called on the new executed version, the first thing main does is it says, hey, do we happen to have an argument? And if we do, handle things differently, and we go down the handling route that way. The next challenge, a random selection of the object type, which defines which virtual function table that we get into each object. Gee, we read in 4 bytes from dev_random. Gee, I've seen that before. We then receive some bytes, and down here, we say, okay, that thing that we shoved in those 4 bytes to as a number, and it with the number 1. What's that mean? It's either even or odd. I mean, you've got a 0 or a 1 left, right? We then test the very lowest byte to see if, we test AL. Advanced question. Can anybody tell me what that does? Bingo. It ends the 2 numbers together, not changing any of the answers, but setting up the status flags so that decisions can be made appropriately. So AL has the number 1 in it, let's say. So ANDing 1 with 1, what's that give you? 1. If it 0 with 0? So it sets the flags and then jumps, if 0, down here. But if not, it falls through to this section here. These are 2 different setup sections which adhere to the 2 different objects that we can create. So, brute force anyone? Truth is, I mean, there's no way to land this thing every time you throw it. You will always have, statistically speaking, 50% of the time failure. However, that's best case. That's assuming you can overcome all the other craziness that comes with the randomness. But because the vulnerability only actually ends up happening half the time, you're stuck that way. So changing anything doesn't make sense, except when developing your exploit the first time, landing it and making it proof of conceptable, so to speak. We can remove dev_random, replace it with a symlink to dev0. Now everything is even. Everything is 0. Or, if we actually wanted to take the 1 path, we just dump a bazillion A's or anything else that's an odd number. What's the hexadecimal representation for A? 4, 1. Yeah, that's why you see it in a lot of my hacks. So if we dump a whole bunch of A's, every 4 bytes is going to be odd, so it'll give us the 1 bit. The random memu was lame, but it was a pain in the butt. And so my team, at the very beginning, we had people in all different directions, and the first thing that I did was sat down and I wrote a client that interacted with it and allowed us to just say, I want to run update. And it would go run update. In fact, I didn't realize how special that was until I was watching another friend give his rundown, and this guy's pretty brilliant, his rundown of the challenge. And in his notes, I saw a comment, buy Atlas a vodka for this, because apparently it made his life easier. Unknown Linux environment. Yay! Actually, this caused me more pain than I care to admit. Turns out all of our testing platforms had NX and randomization. Target environment did not have NX. So if you're running on an x86 386 box-ish, something that's not a Core 2 Duo, turns out NX doesn't work real well. So we were doing all sorts of, return-oriented program madness, and all we needed to do was find a location and land an exploit. We wasted hours. And a chroot environment. Well, kind of, sort of. It turns out that the parameter handed into chroot was /. So we chrooted into root. All right, let's talk about memory a little bit here. Our initial pass, or my initial pass, into identifying how memory got laid out was just simple. I hooked the tail end of every call to malloc, spit out, the call of into malloc, grab the argument, spit it out. So the first argument for malloc is? For a Red Bull that I don't have? Size, thank you. So we've got hex 18, these are all hex, because remember I think in hex. D8, 18, 27, 64, 4, 64, 4, 64, 4, 60, whatever. Another run, we got 18, F0, interesting. 18, 27, 64, 4, 64, 4, 64, 4, 64, 4. That wasn't real helpful. I mean, it gave me an idea, but so I ended up hooking the beginning, grabbing the size argument, hooking the end of malloc, getting the address, and then hooking free. Okay, a friend of mine will actually chew me out. I'm not actually hooking. I'm using VDB to have a breakpoint that runs code and then keeps executing. So slang, that's hooking. It's not what people call hooking. So we dug a little deeper here. 18, this is called from this address and returned that address. Called from this address, we got the D8, returned that address. Blah, okay, not really helpful so far until we get down to here. Oh, wow, we freed it immediately. Then we do a couple more and we free them immediately. Turns out, most of them fall away in the process of the function. So you send data, it creates and frees, but all that we're left with when we're adding new records is 3 things. Turns out, here's our object. See the little endian notation of our VF table pointer and some other stuff, and then the text that I threw in for this example. We then have the textual results of a call to MD5 on our data. So we've hashed our data and shoved that into a hex 18 size allocation. And then we have a struct that ties it all together. So a structure which turned out to be a red-black tree structure. Anybody heard of red-black trees? Show of hands. A couple of you? Okay. Red-black tree is a well-connected tree of storing information that is not the fastest on the front end because it actually jockeys around while allocating to make the search immediately fast. So red-black trees might be good in a database like this. Okay, this is kind of my jizzing all over myself with hex because I got a little carried away. But the things that are more important We have menu items that show up in memory. And even though they're freed, guess what? The data still sticks around until you overwrite it, right? So here, quit, download record, okay, stuff like that. We have record hashes, the textual representation. Remember the allocation of hex 18. We have our record data, which is this pretty thing right here, up to but not including right there. And then we have the glue, the record struct, or the red-black tree pointers structures. So these first three, I like to include the one just because, but these first three D words, they are all pointers to other red-black tree structures. Remember, well-connected. Parent, right, and left, or red and black. We then have a pointer to our hash string and a pointer to our data. Remember, we can always identify it by the VF table pointer. So now what? I can pseudo spontaneously overwrite something. So what do I overwrite? Can I overwrite a virtual table pointer? Maybe. Not yet. Function pointer. Function pointers are beautiful. You overwrite them with an address of something that you want to have executed, and guess what? You trigger that thing and it gets executed. Yeah, we didn't have any of those, unfortunately. So, but wow, that hexadecimal E that I subsequently turned into a hex 200, that turns out to be the size variable. So when you put in this fixed function, fixed object size, you put in a random, an arbitrary size amount of data. They store that very nicely for you right after the virtual table pointer. So if we overwrite that, what thinks we might do? Well, remember, things are randomized, right? We want to drop into our shellcode, not off in La La Land, right? So, came up with a plan. Groom heap memory to open up holes. Remember, we're creating 3 different allocations every time we create a new record, right? We do a lot more, but those are the ones that actually stay. So, when we delete records, turns out the 2 extra allocations, they don't fall away. So we'll create one, and then we'll delete it, and there won't be enough to create another 3 in the space that was freed up. That's kind of interesting. We'll talk about that in just a second. So we'll then overwrite the length field just before a hole that we create. And then we'll view record to see stuff beyond the end of our record, right? Sounds like a good plan? Battle helmets ready? All right, here's our grooming. Create a record and delete it. That leaves a 248-byte hole or something close, depending on which thing that you had there first. Create then 3 records beyond that, and we delete the last one that we created. Then we create 7 more. Basically, it's not to scale, but basically it'll end up like this. Here's our first one that we created and deleted, and you'll see the hex 18 size things falling into there. Then we have our record, another record, and then we've got some more of these things, including a structure with pointers to these data things, right? The structure with those pointers, that's valuable information. So, we do our overwrite. See, I told you I skagged this picture from later. Here's our size. So here's record number 2. Remember, we deleted record number 1. Record number 2 is right here. Record number 3 starts right here, and it's of size E. After the overwrite, however, we keep the VF table pointer, or actually it doesn't matter if it's the right one. We just need to give it a valid VF table pointer. And the one that we want, I'm just using ECC8. Then we do hexadecimal 200 which is way more than we need. And in the very dilapidated, ugly, nasty early revisions of my exploit code that basically reppered any input and shoved it to the screen, or any input from the socket and shoved it to the screen, we get peak data, blah, blah, blah. Oh, cool. You see kind of some binary typey thingies in here, including a bunch of \x's. Okay, kind of ugly, but write a little script to chunk those into 4 bytes that turns them into numbers, and we get something of a bit more value. I wrote a little heuristic algorithm that ran through them all, took the first 20 bits, the top 20 bits, anded them out, got rid of the lower 12, and then shoved them in, counted them up, and found out how many of each we had. And then I said, okay, we're going to say our base address for this area of data is going to be the one that was most common. So 8887, 8887, 8887, 8887, A007, 8887, 8887, 9007. So heuristically speaking, this is the best, most probable area that our stuff is going to fall into, correct? Good. After cleaning it up a little bit, this is what it looks like. Potential peak data found, blah, blah, blah. A different run, 962A, 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 A007, 962A. 962A sounds like a good base. So now that we know that, the evil plan that I hatched was, let's now overwrite the VF table pointer with something. We'll use the same 2 records, second and third. We then access the record using one of the member functions. Remember, I mean, the add, delete, download. These are all things that end up calling member functions on our record. And then, hopefully, if we do it right, we'll land in our shellcode. Are you ready, Fifi? You ready to learn to fly? We'll do custom shellcode for various reasons. Start off with, we think it's chrooted, because we didn't look very closely. And secondly, it turns out we have a space constraint that even Metasploit stuff couldn't get around. So, custom shellcode, very good. Let's take a moment and refresh ourselves on how C++ actually works, after I check how long that I've spoken. All right, we're good. Remedial VF tables. Wow. VF tables are tables of 4-byte in 32-bit case, 4-byte addresses of functions, member functions, right? VF table pointers are pointers within our objects to, specifically, that VF table. You'll notice the 2 tables right here, because we had 2 classes. Here's the first one. Here's the second one. C++ accesses member functions by taking that VF table pointer, dereferencing it, plus some offset. Because it knows what offset into that table is the update function, right? So we deref the VF table pointer plus 12, let's say. We'll use 12 because I said we'll use 12 because, well, that's what I chose later. We can't overwrite the VF table pointer with a function pointer, sadly. That would be awesome, but not. That'd be really cool, wouldn't it? Let's just do a virtual function there. We call into the function with a parameter that tells that function what things we want to do. And oh, that'd be awesome, but it's not how it works. So we overwrite it with an offset pointer to a function pointer, which holds a pointer to the function pointer, not the function itself. Would somebody else like to read that? Because I think I slaughtered it. So basically, it takes the offset into the table and executes that function. jumps into that location. So, how do we do that? How do we get there? Turns out we have to create, or I like to, there are probably other ways around it, but we're going to create a fake virtual function table. And every virtual function is going to point at somewhere that we think is going to be our shellcode. This is where that base address comes real handy. This is, I like to refer to this as transwarp beaming because I realized really early on that things are moving all over at the same time. The location that I'm trying to return into my virtual function pointer is moving in one direction because of the randomness. And the location of my shellcode as an actual address is moving in a different direction. So I thought about Scotty from the latest Star Trek movie, where he's like, dude, we have ship going at warp, and we're, anyway, he said it best. Imagine that. Never occurred to me to think of space as the thing that was moving. So what do? Well, I know what I did. I took the base, and I took I just grabbed an offset. I said, this is where we're going to point our virtual table pointer. So you can move all the freak over you want, within reason. And I'm going to make this virtual function table, so that no matter where we end up, notice the 4-byte changes between each number. Even if this thing shifts up 30 bytes, or 32 bytes, it wouldn't shift up 30. This location will always be where that address points. Really? Think I can do it? So here's another rundown of how this thing all works. We call the edit record. The edit record runs down code which should call VF table pointer plus 12. Also note down here, hex 40 is the @ symbol. I kind of like it. And it turns out it does a great NOP. So here's the code that does it. Here, EAX is our virtual table pointer. We deref that into EDX, so we get the value of it. We then add 12. We then deref that and put in place the location in our function table into the ECX register. We set up some local variables, and then we call our code. Down here in the memory side of things, here's our virtual table pointer. It points right here, 90F2608. It's I picked 90F2574 as the place that, by golly, that's just where we're going to drop. Remember, dereffing plus 12, doomp, 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 4 bytes times 3. And here is the location of our function that is going to be called. 25FC, 25FC. Hey, our NOP sled. I didn't really need a NOP sled, but hey, I got to shove @ symbols in there, and I like it. So we are now executing in our own custom shellcode. You with me so far? All right, let's move on. We don't need a shell. This is a CTF qualification game. Owning things means getting the key on the other side, and they're always called key. So what we really need is shellcode that opens up the key file, reads from that key file descriptor into a buffer of some maximum size, and then write to our socket that buffer of whatever we read in. And then if we're really nice, we'll exit 0. Yeah, I know. You probably thought I was going to ease you into this gently. Nah. So here's the custom shellcode that I wrote. Start jump strings down to here. Call string callback, and this is off the screen. Ugly. Right below string callback is actually the string key. Sorry, it's off the screen. Shows up on mine. So what does this do? String. We jump strings. We call back to string callback. Why? What happens with the call? It pushes EIP onto the stack. Well, what's EIP at the time of the call? Actually, it pushes EIP plus 4, or plus whatever, probably 2 or something in this case. So it pushes the next address onto the stack. Well, the next address is actually the exact key string. So we call back, we pop EBX. What's that do? It puts the location of the key buffer into the EBX register. We then set up the stack. Actually, we set up registers in a way that the Linux kernel will understand what we're trying to do. Why do I say that so carefully? Well, because on BSD, you set up the stack, and then you interrupt. You send an interrupt to the kernel, and the kernel will look at the stack and tell what you want to do. On Linux, it's not that way. In Solaris, it's not that way. You set up the variables in these other environments, and then you interrupt the, you set up registers, and then you hit an interrupt to the kernel, and the kernel will look in the registers for your arguments. It's just a flavor difference. But, so you'll see I push stuff onto the stack anyway and then pop it off because it's easy, cheap, and it doesn't do a lot of additional bytes. So push file mode, pop ECX. Push file flags, pop EDX. ECX and EDX are args 2 and 3 if you start at 1. We then push sysopen and pop EAX. In EAX, when you call an interrupt hex 80 on Linux, EAX is the thing that the kernel looks at to say, what's he really trying to do? So if you called exit, and you guys have probably seen those images where you call libc stuff, but it actually calls the sysexit thing down under the kernel covers. Well, that's what this is. And EBX, well, we set that up here. That is the location of key. So we basically called open key with 2 nulls or whatever we want. I made them nulls for the other arguments to the open function. The results are returned in the EAX register, so we store those in EDI. And now let's read it. Push EDI, pop EBX. We're setting that first argument again. And for reading, we already know the location of buff. We don't need the word buff anymore, so let's just overwrite it. Push, pop. Now let's move from ESI. Remember we stored ESI up here as the file descriptor for our file. Push, pop, ESI into move ESI into ECX. So our second argument is the, where are we? Sorry, the location is the second argument. File descriptor first, location to store is second. And then let's just push, pop, 255. The key file is like 64 bytes, if that. That should be fine. Push, pop, sys read, interrupt 80. We read from the file up to 255 bytes into our buffer that we control. Store the return location, the count, the number of bytes read, right? Because that's the return value of read. In EDI, okay, we're clobbering file number. Why? Well, we don't care about it anymore. And then we push byte 4 pop EBX. Why? Because the file descriptor in this particular socket server, because it's an accepting forking server, is always going to be one number. And in this case, it's 4. Why is that? Anybody, is that not a confusion point? Does everybody get that? Because when you accept in a socket to be handled by the child, it's 4, okay? And then it gets run down through fork, and the child goes off and does something. The parent closes that socket. So as far as it's concerned, 4 is a free socket again. Then loops back up, accepts again. The next one's 4 as well. So this is just a function of what we're doing and how the server works. So we pop 4 into EBX, shove our buffer address into the second parameter, shove our length into the third parameter, call syswrite, and we have now just written the value of the key out over the socket for our client to get. And then, since we're nice, we'll reset EBX, and then call sysexit so that the child exits nicely, instead of tumbling off into segfault. Lessons learned. Know your tool set, know your toys, know what you're doing, and know that you know what you're doing. And no, this isn't a, be awesome because, you need to know everything. No, this is you think you've made it do something. You've had the mental capacity to create something which is amazing. Make sure it's doing what you think you're doing. I have talked to friend after brilliant friend who have quailed at the thought of debugging shellcode, of putting a breakpoint at the thing that either launches into shellcode or somewhere in the shellcode, and then tracing it, when sometimes that's what you need to do. Sometimes your stuff isn't as you intended, and you have to tweak it a little. Know that you know what you know, and know that you know what you don't know. Transport beaming, the art of the fake virtual function table. If you're shellcoding, be careful pushing a word when you mean to push a D word. If you're trying to save space, don't. You save 1 byte, and you leave the upper half of the D word, whatever it was. Turns out, read doesn't like 2 billion as a read max length. I don't know why, but it failed. Take clues from the OS that you're targeting by things that are necessary to run the binary. And if you're doing capture the flag qualification round, try to run shellcode before you go off into ROP nonsense. I'd like to thank my creator, Jewel, Bug, Ringwraith Diva, some personal friends, Scoto, Cutaway, and Masendo, who Scoto and Cutaway and Masendo aren't here, sadly. Invisigoth and Conchoto, Shellfish in last place. Maybe you've heard of them. The Figaro is in the house. My brother's down here. And those who shall not be named. Thank you, everyone.